Something to highlight in your notes then is it would be easy to have forgotten this arrow here, but it's best to put that in. By the way, what would be a good name for this? Well, doesn't this look a lot like an imine? An imine, except it's got a positive charge. Well, we know that when things have positive charges, we call them inium or onium.
Okay.
So this would be an iminium ion.
Okay.
But it looks like an imine, but it's got a positive charge, so it's an iminium cation. Iminium.
And then the alkene is a substituent, or how is that named?
This over here?
Yeah.
Well, this is an aminium, and this is an alkene.
Okay.
And I don't think we'll worry about naming the whole thing. That's probably a little more complicated than you would expect
Okay.
me to do in your class. All we should be able to do is name the functional groups separately.
Okay.
This is an alkene, this is an aminium, and this is an ether.
Okay.
We'll go easy on ourselves and not try to give you the whole thing.
That's fine.
As I said, the cool thing about this is that we formed a new carbon-carbon bond. We're always glad we can do that. Now there's a very specific name for this reaction. This is a reaction we learned pretty early in the course. What type of reaction happened here? In this particular step, what type of reaction was this? This is a reaction from an earlier term.
An addition? Or is it elimination? Oh no, well this is an SN2.
Okay. You know, yeah, I guess we wouldn't call it an addition. An addition is when you get rid of a pi bond.
Yeah, yeah.
But here we're just kind of shifting the pi bond from here to here.
Yeah.
So it's not really an addition, but you came up with the right idea. It's just an SN2. It's a single step attack with a nucleophile on a carbon over here. It's a primary, so this is a good case for SN2. It's just that this is a new nucleophile that you didn't know about when you learned about SN2. It's just a new nucleophile that can do an SN2. So that's the big thing that we should learn now about these enamines. They can do SN2 reactions. Enamines can do SN2 reactions. It's a little bit more complicated than normal SN2 just because of this extra arrow here where the lone pair kicks off the pi bond, but it really was an SN2. Now, remember the whole purpose of this was probably to form this new carbon-carbon bond. The whole goal here is to form this carbon-carbon bond. In many cases, we don't really want to keep the nitrogen around. That was just to make this into a nucleophile over here. So now it would be nice if we could somehow get rid of this nitrogen. Well, what we have here, again, is something that's very closely related to a imine. And now we can use that hidden carbonyl idea that I was talking about before. Imines are what are produced from category 3 reactions. That means that they're hidden carbonyls. And there's an easy way to treat any hidden carbonyl to make it revert back to the carbonyl. It's been a while since we talked about that. Do you remember what's the simple reagents that we need to add to a hidden carbonyl to turn it back into a carbonyl? What do we need to do to put the carbonyl oxygen back on this carbon? Where would the carbonyl oxygen come from that we would put back on this carbon?
Would we add H3O?
H3O plus.
Yeah.
That's right. Remember that the carbonyl oxygen left as H3O plus. So it would be natural to put it back on as H3O plus. So we can reveal hidden carbonyls just by adding H3O plus. So let's go ahead and do that. And I think I'll just show you, maybe you can work that out, but at the same time I'll just show you what would happen here. Maybe I'll use the redraw and modify technique again. Well, I'll just draw like this. Now the key thing is, this is the hidden carbonyl carbon, so it's going to have to turn back into a carbonyl, which means that these two bonds are going to have to be blasted off. Where did this oxygen come from? It came from the H3O plus, and this has been completely blasted off. That might seem weird to people that we can just cut off this great big component here, but that just gets blasted off. We won't go through the mechanism for that right now. And I guess we could also say that since that's left, the nitrogen would have to gain a proton to stay neutral as it's leaving. So this would be what that would look like after it leaves. Very minor technicality, we know that under acidic conditions, amines actually get protonated. So this would be the best way to draw this product under these acidic conditions. That's not what people really care about. What people care about is this product. Now notice what's happened overall from our original starting material. Here was our original starting material. We started quite a while ago, but we started with this over here. And we did a lot of changes, but overall, all that we've done is we made the alpha carbon into a nucleophile and had it attack this carbon over here. The whole point of this whole great big apparatus was just to add this new carbon chain to the alpha carbon. So this whole scheme is a way to make the alpha carbon into a nucleophile and have it attack. We already know another way to make alpha carbons into nucleophiles, which is to make them into enolates. We could also make this into an enolate, but sometimes an enolate is too reactive. Sometimes you want a more moderate nucleophile like an enamine. So this is an alternative to making this into an enolate. Okay. Rather than making this into an enolate, if we want a more moderate nucleophile, we can make it into an enamine. So let's look at this all in one grasp. What we wanted to do was add this carbon chain to this alpha carbon.
Correct.
So we needed to make this nucleophilic. So how did we do that? Well, we treated it with this to make it into an enamine, because we know that in the enamine, the alpha carbon will be nucleophilic. Then we could add the carbon chain, but all of that would be useless unless we could go back to the carbonyl. Well, that's no trouble, because we can just add H3O plus to get back to the carbonyl. So it's important to be able to see overall what we did here. To make the alpha carbon nucleophilic, we treated it with the secondary amine to make it into an enamine. Then it was a nucleophile, and you can do the SN2. And then we just have to remove this nitrogen with the H3O plus. And the whole purpose of this was to add this carbon chain. So this is the product we were going for all along. I've drawn two arrows here to show that these will be two separate steps. Okay. First this step, and then this step. And we need to predict the products. Now, we probably don't want to show all the mechanisms here to save time, but we should try to show, what should we try to do here? We should try to show the product from each step. We shouldn't just go to the final product here. Let's try to show the product from each of the intermediates. And, actually, why don't you show the mechanism for this first step? That's not that complicated. Let's show the mechanism for that first step, if we can come up with it. So let's think about what would happen first between this reagent and this. That's a good start.
Bless you. Do you want me just to continue?
Oh yeah, sorry.
Okay.
Go ahead. Very good.